about the analysis, although there's a very big title there, but it's more about the users and how, I mean, a particular type of users, but how we are big users of SST, but how we're more and more going into the high resolution SST, so sort of colliding with this group, which makes me very happy since kind of organized my two lives, scientific lives. I work for Farallon Institute. We are a small organization that does marine ecosystem research. And I'm the physical oceanographer there, or the person that runs all the data, and mostly working on SST. But so let me tell you why I'm giving this talk, which is completely different from the rest, I think. I work for marine ecologists, so this is the particular kind of user that I work with, and this means that they study a specific marine ecosystem, and so there's no one species. Usually, there's many. And the only way to do that is usually with a very long data, trying to understand how the ecosystem functions. So what they want is long time series of data, which are all know in the ocean, they're hard to get. But it's a lot of fun. And for that, when we try to connect with the environment, we use a lot of sea surface temperature data. Obviously, there have been many time series that are very long and that match what we have from the ocean. But also it's measurements when we don't have other measurements, right? Because marine ecologists as well as biologists, they love to go to places very, very remote where there's no humans, or trying to get to where there's no humans. And obviously it has been one of those best resources so far to understand this. And since they have been applied for climate change impacts, we use them with confidence in a way. However, well, we know that there's issues with accuracy or even availability very near shore, in particular in coastal regions and in combination near shore and Arctic regions, which is why my group of ecology colleagues care about. So why coastal areas? I don't think I have to beat the drum about why they are important. But beyond the human interest in coastal areas, I want to just say why in particular our group is very interested in this, and not just the group, but many other marine ecologists. Basically because they are areas of very big nutrient entrainment, right? And that figure just shows chlorophyll concentration in coastal areas in the American continent. And you can see the highest concentrations are near the shores, either by runoff, upwelling, some sort of coastal interactions. And that's where then most of the life in the ocean is located because of this nutrient entrainment, right? Like that's where the phytoplankton blooms happen. This is where things concentrate. And in particularly, there's a group of animals that we're interested in that are the seabirds and marine mammals that use land because they live near the ocean, near the coast when they are breeding, and they use land usually for breeding, right? Like the seabirds nest on islands and coast, and marine mammals as well. And they have a limited range of forage when they are breeding, right? Like they go on average 200 kilometers offshore. Some of them can go very far. Some others like just stay very near the shore. But they utilize this coast very, very hardly. Or yes, I don't know if that's the right word. But one thing about these data sets that is very interesting for ecologists is because it's one, I mean, it can be one species or at least one group of species, but they can be very well measured, right? Most things in the ocean, fish, zooplankton, whatever, they are moving around and it's very hard to go and measure. You have to go with a ship or some sort of remote sensing, but I mean, not satellite, but like gliders or something to measure it. And it's very difficult to know if you're capturing everything that is out there. However, seabirds and sea mammals, marine mammals, they do go and find whatever they need to eat. So they are reliable indicators of what the ocean is doing, but also they come to land, so we can actually look at them and at over land and measuring pretty accurately, right? And so that's why we use them so much as indicators of what's happening in the coastal ocean. They are good indicators of the ecosystem health because their diet indicates how good or bad certain species work, how good or bad they reproduce. Each year indicates also how the ocean conditions are doing and if the food is there for them. Um, So in this talk, I'm going to talk about the project that I'm working on. But I mean, we have many of this kind, and especially they're becoming very global. And so I'm going to focus on one just to give you an example. But this is work that we have done with this group for 15, 20 years. And so in different sites. And now we're combining all this information into global. And in a minute, I'm going to talk why now we're going into high resolution sea surface temperature. So the project is about global change in seabirds' reproductive success, how many chicks and how much they survive in relation to ocean climate change. We started this a few years ago um, by combining initially a lot of time series around the world. We have over 60 or 70 sites around the world, but we're now selecting specific prime sites or premium sites. What we are defining by, we have many species in the same site, so we can measure different types of species that can react differently to changes in the ocean. And also that they have long time series, because the longer time series we have, the more perspective we can have in their change, especially with respect to recent times, right? Like we can separate what's been happening in the first initial decades versus the last decades when there's been a lot of change. Now, this is not explicitly a criteria, but many of these sites are away from human interaction. I mean, that's why they tend to be premium sites. That's where there's a lot of species there. But that also gives us a perspective of species that have not been directly influenced by humans in their habitat. So that gives us a little bit more understanding of the ecosystem and how it is changing. Just as a reference, sorry, it's a little bit hard to see from here to there. The medium time series length of these sites, it's about 35, 36 years. So that's why we are looking always for long time series of data. And just to, as an example, this is not actually one site that we're looking at, it's South Africa, but this is kind of the look of this size, right? There we have several types of birds there. There are marine mammals in the background. And then you have the biologists that go and measure there for a few months, a year, and they record how many nests there are every week and how many eggs and then how many chicks. And then they go back to their labs or their offices and process all that data. And what they give you back is 1 point per year, right? And I'm stretching this because it's been one of the hardest things to do when working with ecologists, because they want to do all this analysis and tell you, oh, I want to do blah, 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 and then they give you 5 points and you don't know what to do with them. But luckily, that's why we're looking at places that have long time series and many sites so we can have the most um, data points. And now the other thing is they come very excited and be like, oh, I saw this talk about sea surface temperature and there are this amazing data set with high resolution and I want to integrate that to my research, right? And they want to take this daily sea surface temperature around the world and then match it to their 1 point in one site. And so that is a very big challenge on how to do this. So initially, I'm a physicist, so we start with spherical cow. We start with points, things that are very simple. We started with just high resolution, global data sets that do not have a lot of resolution, but long time series. We started using Hadley, eventually optimal interpolation SST, because we're looking at changes in the global ocean. And some of the first results show that there are differences in the birds in the northern and southern hemisphere. But now that's not enough. Now we want to know what is the relationship with their sites. And so then we zoom in the sites. And so the sites are there with a 200-kilometer range of where these birds forage. And I hope you can see them because I can't. But that's kind of my point of this plot. Like, once they tell you that they want this amazing data set and you plot them, they're like, well, I can see anything. I'm like, yes, this is how small your area is, right? And sea surface data from remote sensing at coarse resolutions really cannot see those little points there either. So I'm just zooming here just to show you more or less how these sites look. They are just amplified. And also to show you, I mean, to be able to see where they are, a lot of these sites are very high latitudes, basically because those are the remote areas, and especially in the north, they're very rich areas for marine ecosystems. So we have a lot of time series for a very long time in these areas that are some in Antarctica or very close to it. There's not a lot in the tropics and subtropics, partially because there's not been a lot of research. However, there are many time series that are starting to get long. So in a few years, we're gonna get to this point that they are long enough to do this ecological research that we do. So we're also gonna add some of those. Many of the time series that we have is in the bigger time series that are not premium size are there, but there's also more human interaction and confounding things. But this is kind of the data that we do. And you can see here how different is, I mean, the colors are the sea surface temperature climatology for these sites, and the gray are the coastal areas. And you can see how different also the coastal area or the coastal geography is with respect of the area that we are looking at, right? So that's another challenge, the mask that we have for land, how they interact with the sites that we do. So what are we data needs for this kind of work? Again, we started with using global data, right, all the ocean, but really these birds during the breeding season in particular, they don't go to sample the whole ocean, so they're very, very close to the coast. So we need coverage at the coast, which already like the big or the coarse resolution data sets didn't help us very much. And then the other thing is that we need big data extent. And we want obviously accuracy and precision and availability and access to the data, and in a user-friendly way, because most of the users do not talk NASA acronyms or sea surface temperature acronyms, and it's very hard to understand which data set is which. And more, we're starting to want high resolution sea surface temperature to be able to observe ocean features like fronts or marine heat waves that do not reach the coast and create some fronts with upwelling, with river plumes, et cetera, et cetera. So we are studying right now or starting to play a little bit with data. As I say, optimal interpolation SST is the one that we've been using, but actually we've been using it in monthly time scales, which has been coarser resolution, but now we have changed to daily. And we're also going to use Muir and Ostia, which have much more resolution, but you can see the period of study, it's much shorter, and that doesn't give us really the perspective that we need. However, we want to start working with this, and now with the talks that I've listened about these other data sets coming, I'm really excited that this is possible even sooner than I thought. And so first of all, thank you very much to this group, because really they are making our work much more interesting and my particularly much more easier. And I'm very excited that that this coastal importance for SST in high resolution is really taking off. I started working with very coarse data, and it's been a battle talking to the ecologists all the time. So I'm gonna go very quickly just through this slides. There are plots of trends, but it's not so much about the results, but about the difference between the sites. So I mean, this is the kind of things that we initially are asking, right? Trends in how things change, and these are the very basic questions that we're going to do. This is just a daily structure, how it's different from different sites, but I don't need to tell you about that. You are very familiar with these data sets, but these are the change in the seasonality between the high resolution data sets, OSIA and Muir, compared to OSST. And just to show you, I mean, what we expect is kind of flat lines, right? Like the products are pretty much the same, but you can see that there are some sites that have high differences, and not unexpectedly, those are in the Arctic and in Antarctica, but there are some that are like in Japan, for example, or Russia, which are also some of them high latitudes and have particular challenges in the coastal ocean. So it's a challenge for me in particular, but for the ecologists in general, how to consider this data in comparison with others that are very flat, right? Like some places where the data is very accurate between or among data sets, and other areas like which one I choose, because they are very different types of coastal environment. Then these are the trends for SST. The colored ones are the different data sets, and you can see that they match more or less okay for all sites, which is great. And this is just averaging SST for the entire 200 kilometers and showing. And here there's a gray one that I'm showing not just to make a point. This is the optimal interpolation SST from the 80s to now. So it's a longer data set. That's why the size of the trend is very different. That is obvious since it's more data. But the way that what I'm showing you here is that why this long time series is important for us, because obviously it changed the perspective of how things are changing. We are really interested, obviously, what's happening with birds or with the ocean right now, but we need to put it in perspective of what's happening before, which obviously was very different, right? There is a big change, which we have heard a lot about yesterday. So they agree very well, but then when we go to trends in the maximum or the extremes, and for this I'm using 95 percentiles, we're starting to see differences, and these are one of the measures that we use for marine heat waves. And again, this is a very coarse level because it's for the entire region, but you can see it's starting to get some difference between data sets. I mean, particularly Ostia has some areas when we have high variability and others not, but it's hard to tell which ones are right. I mean, between sites are differences. And then if you go to the lowest percentile, which is relevant for the previous talk, like when we have cold spells or cold things, trends are starting to get a little bit more dicey, right? And particularly in areas when there's ice, which obvious, but we have several sites that are very cold and with ice, and we are very interested in understanding those processes. So just a quick summary, but it's really more like almost like a petition for the group. We are starting to see very great data sets with high resolution SST, and we're moving forward now to understand how the structure within these 200 kilometers coastal areas are important for the birds. The fronts and changes, as I say, with marine heat waves are very important, but we need to be able to see it in high resolution. Otherwise, it really doesn't tell us much more than what we had before. But obviously, we want long-time series. And so, again, I'm very excited for these products that you guys talk about in the last few days. And then how to compare different places. And this is a question that I kind of posed yesterday, like which data set we use. And to me, when I see validations tend to be in different places or specific places, but then we have a range of places, many of those when there's no in situ data to validate, which is, it's hard. So it might be interesting to connect to some of this product to work on places that we are interested when there are interest for biology or ecology, and maybe try to do some extra validations there. And of course, it's one thing that it has been very hard for us to do is extract time series of our data. We are not, the group is not an expert coder, right? And particularly not expert in the new technologies, and getting time series, it's very hard. It takes a lot of effort and time and storage. And so I wish there was easier ways to just extract time series and not just a snapshot. So that would be my last plugin. Thank you.
Questions? Owen?
Much time here.
A comment on your last point there. The SST CCI dataset, we've got a website where you can download extracts for small regions or time series, surftemp.net, and that'll be 1980 to present.
Yes, I'm super excited about that. Thank you.
I just have a comment. Are you familiar? There's some group, and I'm not sure if it's University of Heidelberg, but they've been putting sensors on seals and penguins in Antarctica, and they're getting really good SST measurements. They're dense and stable. It's not a very long record, but they're getting amazing results. So
Yes, I mean, there are many of this data from different animals, which are always super cool and charismatic but as you say, they're not long records. They are not year-round. They're very expensive and very sparse. So they don't help us for our purposes, but for validation they might, and so that helps.
okay.
We have a question online from Chongyuan Mao. And then just a kind reminder for everyone in the room to introduce yourself, your name and your organization, just so people online can follow.
Hi, it's Chongyuan from the Met Office. So I think Helen actually put a very long,
We
good
can
description.
Yeah.
Sorry? You can hear?
Can we hear you? Yeah. Go ahead.
Can you hear me now? Okay, great.
Yeah.
So I just noticed Helen put a very long description in the chat as well after I raised my hand. Just to reiterate, like there is, apart from CCI, as Owen just mentioned, there is a reprocessed SST products as well available in Copernicus, which are also based on Ostia. And the difference between these two versions is the Copernicus version is basically the same as the near real-time Ostia in terms of its foundation SST, and pretty much the observation probably not exactly the same. The CCI version is set to 20 centimeters. So if it matters to you, then, for some research, maybe the representation of the SST matters. So that's one difference. But that one, the reprocessed Ostia SST available from Copernicus is from 1981 to 2022, I believe. So that could be a good thing to use instead of the one you just showed in the table. I think that's near real-time Ostia. Because the reprocessed version will be more consistent as well. The near real-time will contain any operational change we made when producing the data, and it could also be affected by some data being degraded. There's like daily change. So the reprocessed version will be sounds like a really good one for you to use. And also, I think there's also some observations on the mostly northwest shelf and around the UK. They put Argo sensors on seals, so it could also be something for like a localized observation that they can use. That's all. Thank you.
Thank you.
And maybe one comment from me, Johanna here from DMI. I believe, Marisol, that if you go to the Copernicus Marine Data Store, first of all, you can discover a lot of these data sets that were just mentioned, the Ostia reprocessed, the Ostia multi-year. I think if Remer delivers the Odyssey multi-year as well from 82, so there's there's another product to look at. But they also now have the capability to extract time series from the Copernicus Marine Data Store. So I think you just need to sign in, make an account, and maybe you can easily pull out time series and select the product and pull out time series. That's all.
Thank you. And unfortunately, we have had some problems extracting the whole thing. We have tried, and then I don't know if it's the distance, the connections get broken once in a while, but yes, we're excited to get in there. Thank you.
Okay. So let's thank Marisol for her talk. And next we have Pia Englyst from DMI.
Hi, everyone. Perfect. Today, I'm going to present an application study where we use satellite-derived surface temperatures to benchmark climate models and reanalysis in the Arctic. And this study has been done in collaboration with many colleagues at DMI. I don't know, that was fast. As you're probably all aware of, climate change is most pronounced in the Arctic, and with a warming rate much higher than the rest of the world. But despite much attention, there has actually been limited consensus on the magnitude of the Arctic amplification over time. Sorry, I don't know. a bit weird. In 2016, most research showed that the Arctic was warming about twice as fast as the rest of the world. And in the sixth assessment result by IPCC from 2021, they stated that it's very likely that the Arctic has warmed more than twice the global average since over the past 50 years. And later the same year, the Arctic Council affirms that the Arctic is warming about 3 times the global average. And now the latest research shows that it's actually closer to 4 times the global average. And they show or indicate that the previous studies have been seriously underestimating the magnitude of Arctic amplification. Even today, there are large differences and uncertainties in the Arctic surface temperature estimates, and there are limited consensus on the magnitude of the Arctic amplification among the different models and observational-based datasets. But why is it so challenging to provide accurate surface temperature estimates of the Arctic? There are many reasons for that, and here I have identified 2 key challenges. The first one is related to the large temporal variation in the sea ice cover, in particular the large reduction in the sea ice cover, as illustrated in the map here in terms of the trend in open water days. And you can see that the Arctic is generally experiencing more and more open water days. That means that there are some areas that were previously mapped as sea ice that are now shifted towards the open ocean. And why is that challenging? Well, as you know, there's traditionally been, or the sea and sea ice surface temperatures, they've traditionally been derived and analyzed separately. And it's pretty hard to calculate a trend over an area that keeps changing in size and shape. And another problem arises that most of the existing observational-based datasets, they use a mix of sea surface temperature over open ocean and near-surface air temperatures over the sea ice. And that also complicates the temperature trend calculations, as the temporal variation in the sea ice cover will result in a shift in the variables, and that may introduce artifacts in the climate dataset, and that is clearly undesirable in the context of climate monitoring. The second challenge is related to the very sparse in situ network in the Arctic, and that limits the number of observations that are available in the observational-based datasets and to reanalysis. And currently, none of the reanalysis or observational-based datasets, they don't take into account the satellite-observed ice surface temperatures. So that means that they are actually based on very limited information in this very sensitive region. Therefore, there is a need for better surface temperature estimates to enable us to better benchmark climate models, but also to better represent and monitor the Arctic warming and amplification. At DMI, we have recently developed the first daily gap-free combined sea and sea ice surface temperature climate data record of the Arctic. So this dataset is really the mother of the dataset that Joanna presented yesterday, where we're expanding to global coverage. So you can see from the map, it covers both the open ocean, the sea ice, and the Magellan ice zone of the Arctic. It is based on clear sky satellite observations, and the gaps due to clouds are filled using optimal interpolation to provide the daily gap-free fields and corresponding uncertainties. So this combination of sea and sea ice surface temperature brings a new possibility for consistent climate monitoring in a region where the sea ice cover is declining rapidly. And here I've shown the trend in the monthly anomalies of the combined sea and sea ice surface temperature, and we have a total surface temperature increase of 4.5 degrees since 1982. And you can see from the map that the temperature has not increased the same everywhere. We have a peak warming in the northeastern Barents Sea of up to about 10 degrees. So this dataset provides new spatially detailed information, and it's an important supplement to, or it can be an important supplement to in situ observations. In order to better supplement the in situ observations that measure 2-meter air temperatures, we have investigated the potential of converting the ice surface temperatures to near surface air temperatures. And that has been done using an empirical model, which was originally developed in a Horizon 2020 project called EUSTIS on clear sky surface temperatures. And in that case, we trained and validated the empirical models against in situ observations, and we derived separate models for the sea ice and for the ice sheets. And the animation just shows an example of the satellite-derived 2-meter air temperatures compared to in situ observations. That is the circles you can see. So we used the same model to derive daily gap-free 2-meter air temperatures over sea ice, and for the full record back to 1982 and up to now. And we have validated that using the same in situ observations that Johannes showed yesterday. And you may recall that Johannes showed mean differences of several degrees compared to these in situ observations that measured the temperature 2 meters height. But now that we have converted the ice surface temperatures to 2 meters temperatures, these mean differences are reduced to below 1 degree. And the graphs, they illustrate just an example from one of these buoys, the temperature from the satellite, the IST in the top and the 2-meter temperatures in the bottom against in situ measured temperature, that's the black ones. And we see a much better agreement after we have converted it to 2-meter temperature. If we use the same in situ observation to validate AR5, we find that AR5 is too warm. And that is a problem because AR5 is often used in climate assessments and for model evaluations. And that can lead to wrong conclusions, such as assuming that the climate models are too cold. And this has actually been the case. It's known as the long-standing cold biases in the Arctic, and it's seen across all the CMIP phases. Shown here is the CMIP 3, the CMIP 5, the CMIP 6, and the high-resolution CMIP. And you can see that in the Arctic, they all show biases or mean differences against AR5. They are cold by 2 degrees, and it's significantly larger during winter of more than 4 degrees. And traditionally, climate models, they have only been validated using reanalysis datasets. If we use our new satellite-derived 2-meter air temperature as reference instead, that reveals a whole other story. Here we have compared our satellite-derived surface temperature, near surface air temperatures, and compared them to AR5, that's the middle plot, and CMIP 6 to the right. And we can see that AR5 has a warm bias compared to the satellite observations of several degrees, while the CMIP 6 actually agrees quite well in the central Arctic sea ice. And that was, so this spatially detailed information from the satellite observations that can be used to evaluate the models and improve and guide future developments, but it may also provide a better representation of the Arctic warming. The graph here shows the Arctic warming in the bottom one, in our data set, sorry. And the blue and the red ones, that's the difference of the CMIP 6 temperatures, the blue one, and the red one is AR5. And you can see here again that AR5 is consistently warmer than the satellite-derived temperatures, while the CMIP 6 has a mean difference around 0 throughout the time. But you can also see that in both cases, they underestimate the warming rate compared to the satellite-derived temperatures with about 0.2 degrees per decade. So if we replace the temperatures over the Central Arctic sea ice in AR5 with our observations, we actually see an increase in the Arctic amplification from 3.8 to 4.2 degrees. So these initial results indicate that the Arctic amplification is still underestimated in AR5, and they demonstrate the value of having spatially detailed information observations over the sea ice. So to summarize, we have developed the first gap-free combined sea and sea ice surface temperature climate data record for the Arctic, which enable a consistent climate monitoring of the region with the sea ice declining rapidly. We found that on average, the temperatures increased with 4.5 degrees and a peak warming in the northeastern Barents Sea of up to 10 degrees. And we have used these satellite-derived ice surface temperatures to derive 2-meter air temperatures. And that provides new spatially detailed information over the sea ice, which can be used to benchmark climate models and reanalysis and to guide future developments in these products. And it also brings new insights into the Arctic warming and amplification. And in case you want to learn more about this, it is published in this paper here by Tian. Yes, I think that's all for me. Thank you.
Thanks, Pia. Any questions for Pia? Yes, please.
So I'm François Roy from Environment Canada, I work in ocean modeling. So I was wondering, in the context of model evaluation, atmosphere, ice, ocean, how these new ice surface temperature and 2-meter air temperature measurement, how are they totally independent of the snow and ice properties? Are they totally independent? Can we make this assumption when we evaluate our systems?
So the product provides the temperature of the surface, yeah, and it doesn't care if it's snow or if it's ice. So it's the surface, it's the skin temperature that.
So in the retrieval, there's no assumptions about.
No.
Okay. Thank you.
Yes.
Yeah, I just try to provide a comment. My name is Bo Yinghua from NOAA NCI again. So NOAA NCI, we have a NOAA global temperature. It's version 6. That is using the air temperature over the ice over the Arctic region. So that means north of 60 degree north, we are using the air temperature instead of the sea surface temperature. So that way actually is very kind of similar to what you presented. The difference is we are using the in situ observation from ice buoy or nearby island stations instead of your 2 meter from satellite observations. So I think we can collaborate or have a kind of intercomparison to see what kind of difference.
Yes, definitely. So I think that's the whole point. Like there are very few in situ observations. So if we can somehow learn from the satellite observations to supplement these, then that would be very good.
Yeah, the point is I agree with you that Arctic region, we cannot using the sea surface temperature to assess the warming rate because over the ice, sea surface temperature is kind of constant. So the warming rate is always underestimated.
Yes. I think I would prefer to just use the surface temperature, like also over the ice instead of the air temperature, because then we are again introducing this shift in the variable going from the air temperature over sea ice to sea surface temperature. So in the perfect world, it would be the surface temperature in both cases. I think that would be most consistent when monitoring the warming in the area.